Hello and welcome to H2OQ. I'm Professor Dale LeCaptain from Central Michigan University and co-designer of the H2OQ backpacks. We put these packs together to offer you the opportunity to take chemistry out into the field and enjoy the transforming power that it offers. The backpack's brought to you by the generous support of the Dow Foundation, American Chemical Society Midland Section, and Central Michigan University. We hope you enjoy the transforming power of chemistry, brought to you by H2OQ.
Hi, I'm Eileen Buckestein. I'm the Education Coordinator for the Lower Grand River Organization of Watersheds, and I'm here today with my student friend Jack to introduce you to LGROW's Blue Crew program. So this is a program for students to perform water quality analysis within the Lower Grand River watershed using the H2OQ backpack, plus some additional materials brought to you by NOAA, the National Oceanic and Atmospheric Administration. So we're going to start out by taking a water quality sample out of the creek. Okay. We'll be sampling several water quality parameters today. It all begins with taking a good water quality sample out of the stream. And so, first of all, we need to remember safety. If you're wearing boots like I am, you shouldn't go in much above your ankles. If you're wearing waders, you shouldn't go in much above your knee. And that's just to make sure that you're safe in the stream and you're not gonna fall or trip in the water. So, I'm gonna go out and take a sample from the stream. It's important that when you go out, you take your sample from just upstream of where you're standing so that any sediment or anything you've kicked up by walking into the stream doesn't get washed into your sample. We're also going to rinse each of our sample collection bottles 3 times with water from the stream before we actually collect and save the sample in order to make sure there's no contamination from something that might have been in the bucket or the bottle previously. This bucket already had water in it, so I'm going to dump it out. All right, so I'm going to collect a sample in this bucket, and then I'm also going to collect a sample in these bottles for some of the parameters that we'll be sending out to a lab. Some things are hard to sample in the field, so we're sending out samples for total phosphorus, total suspended solids, E. coli, and what's the last one? Chlorides. So first I'm going to collect my water sample for what we'll do our other tests with, our field tests with. So here's my water sample for our field tests, and then Jack is going to hand me the bottles. These are for our lab tests. You want to fill these as much as you can, get as little air gap as possible in the top, and then you're going to place it in your cooler and keep it on ice until you're able to deliver your sample to the lab facility. Now, our E. coli sample is going to be collected using a special tool called a Whirlpack. Now, this looks like a plastic bag. This is a sterile bag where you should always handle gloves when you use it. You're going to tear off the top of the bag. Using gloves, open the bag and drag it across the surface of the creek to collect a sample. Try not to touch the bottom of the creek at all. Your bag might look a little bit smaller than this one. Then you'll seal the top of the bag, and it closes a lot like a dry bag. So you'll twist the top until it feels tight, and then you'll twist the top around and put your sample bag in the cooler along with your other samples. So the last sample that we are going to collect at the stream right now is one that is not going out to the lab, but you're actually going to take back and you're going to store it in your classroom and analyze it 5 days from now. And that's for biological oxygen demand. So just like our other samples, we're going to rinse the bottle 3 times with sample water. And then we're going to fill the bottle all the way to the top. Now this bottle is very important that it's filled all the way to the top, and when you put the cap in, that water spills over the side. This ensures that there are no bubbles in the water that would disrupt your oxygen reading later in the week. So once you have this sample collected, you're going to place it in the cooler, and then you're going to take it back to your classroom and you're going to put it in a cool, dark place for 5 days, and then you're going to sample the dissolved oxygen in this bottle using the technique that you'll learn later in this video. All right, now we're going to take our sample water over to our testing area, and we're going to perform our chemical field tests. All right, now that we have our sample, we can start to perform our chemical tests. Jack has set the cooler aside. Those are the lab samples will all be taken to the lab after we're done with our field sampling today, so we don't need the cooler anymore. So the Blue Crew program looks at 9 water quality parameters that help us determine an overall index of the health of the stream. So the first thing that we're going to test today is dissolved oxygen. It's very important with these chemical tests in the field that you follow appropriate safety procedures. So you'll notice Jack and I are both wearing gloves, and we both have safety glasses on. For each of these chemical tests, it's very important that you wear your gloves and your glasses in order to protect yourself from some of these chemicals. We also have 2 waste containers here. This waste container will take all of the waste water from our procedures, and then this can be dumped down a drain, a sink, back in the classroom or at home. Don't dump this into the stream or in the field, but it is safe to dump down the drain. This second receptacle is where we'll put any trash or garbage that's generated from our testing procedure today. So I'm going to take a smaller sample out of this big bucket just so that I don't have to have the large bucket on the table. Again, I'm going to rinse this container 3 times with the sample water before I take the sample out of the bucket. And we can set the larger bucket aside. Thank you, Jack.
Of course.
All right, so out of the backpack, I am going to take the dissolved oxygen test. So the dissolved oxygen test comes in this longer container. This one is the most important that you wear your safety equipment while you're using the test. And I'm going to walk Jack through how to perform this test. So you can go ahead and open the test. We have some sample water here to use. The first thing you're going to do, Jack, is you're going to take out this glass bottle and remove the stopper. So just like with all of our other sampling that we've done today, Jack is going to rinse this bottle 3 times in this sample water before taking the actual sample. Very good. Next, he's going to fill the bottle all the way to the top. He's going to fill it so full that when he inserts this glass stopper, a little bit of water spills over the side. Since we're measuring oxygen, we don't want any bubbles to get collected in this water. Very good. Very good. All right, now we're going to use a series of reagents to have a chemical reaction occur that allows us to assess the health of the water here. So the first step is to take out the manganese sulfate solution. So we'll read all of these little bottles here are labeled. Probably should have had them lifted the right way. All right, so the manganese sulfate solution is the one that has the yellow top. So you're gonna add 5 drops of this solution to your sample container. All right, next we're gonna add 5 drops of the alkali azide reagent. And you can see the colors start to change. Now we're gonna put the lid back on, but we don't want to trap any oxygen in the container, so I'm gonna pour a little bit of sample water into the top. And then Jack, I'm gonna have you put the stopper in, and you'll notice a little bit of the material, the liquid, will spill over the sides, and that's good. Perfect. Now Jack, you're gonna invert the bottle a few times so that it starts to mix. And you'll see the sample is starting to become kind of orangish yellow, kind of cloudy, and there's what we call a precipitate forming inside. Very good. All right, now Jack, you're gonna set that bottle down. We're gonna let it sit for about 2 minutes until this precipitate settles out and the sample becomes limpid, which means that it's clear and see-through at the top of the sample. So while we wait for that to settle, we can talk a little bit about why we're sampling dissolved oxygen. Oxygen is really important for us to breathe, but also for the organisms that live in the water to breathe. So if you have low dissolved oxygen, you probably don't have healthy aquatic life in the stream. And oxygen enters the water from the air through things like these little riffles, these water splashing that we see in the stream here. So colder water tends to hold more oxygen, and warmer water tends to hold less oxygen. So now we can see that the precipitate has settled out to the bottom of the container and the top is totally clear. This is what we call limpid. So now we can move on to the next step of the test. So Jack, if you want to remove the lid, the next thing we'll do is add 10 drops of a sulfuric acid solution. So again, this is why it's so important that we're wearing gloves and safety goggles. So Jack, if you want to add 10 drops of the solution. And as he adds that, you can see precipitate starting to form again and some color starting to change. Now you'll put the stopper back in the bottle, again slowly, carefully, trying not to get any air bubbles in the container. Very good. And then you will invert it a few times. And you can see, if you want to hold it up, the color has changed to this golden yellow color. And we have kind of an orange precipitate in there. So what he's going to do now is invert this bottle until all of that precipitate is dissolved. The more dissolved oxygen you have in the water, the longer it will take for this precipitate to dissolve. Sometimes it can take up to 10 minutes, so you might want to take turns inverting it if you get tired. So over the course of a few minutes, as we've inverted this bottle, you can see that golden orange color precipitate has dissolved, and now our bottle is totally clear, limpid yellow. So we're ready to move on to the next step of the experiment. This is where we are going to perform a titration, which is a pretty fun part of the experiment. So we're going to take out this little plastic cap that has a little hole in the lid. Jack, I'm going to have you remove the lid to the dissolved oxygen bottle. And then you, just like before, are going to rinse this bottle with a small amount of that yellow sample container. So this is not going to hurt you if it touches you, so don't worry about that. Pour a little bit in, swirl it around the bottle, and then dump it into our waste container here. And you're going to do that 3 times. Yep, very good. Very good. Now you're going to take the sample, and on the container here, there's a 5 milliliter line on the bottom. Fill this container up to the 5 milliliter line. Very good. Now you can set that bottle, the glass bottle, aside. That's extra in case we want to perform a second set of tests, or if we mess up, which sometimes happens. You can go ahead and put this lid on. And then the next thing that's going to happen is we're going to add 1 drop of this starch indicator solution. Yep, so you'll add 1 drop of the starch indicator, and you'll notice a change in color from yellow to violet blue. And you can gently swirl the container till it's a uniform color. Very good. And then go ahead and set that on the table and put the starch indicator away. So now we're going to perform the titration. So we're going to take out this titrant solution, and I'm going to add this little pipette to the bottom of this syringe. And I am going to pull up, how much? 1 milliliter of the titrant solution into the syringe. So I'm going to pull it up until the plunger here is at the 0 line. So when we perform a titration, what he's going to do is he's going to add 1 drop at a time of this solution into the container, into the purplish blue solution, and gently swirl after each drop. He's going to do that until this solution changes from dark violet to totally colorless and clear. So swirl a little after each drop. There we go. You can see the color is starting to lighten. He's getting closer. So once you get close to the end like this, can I take this just for a second? You might look at this and say, oh, this looks like it's totally clear. I'd recommend placing it on top of a totally white piece of paper, and then it's easier to tell whether or not your sample is clear. Usually what happens is we think it's clear, and then we say, maybe we should do 1 more drop. Swirl it around, and then you say, oh yeah, now it's totally clear. And when you set it on the paper here, you can see totally clear. So what we'll do then is take this plunger, and we can see the point where the bottom of the black plunger will read the number that it's next to. Here it's next to 0.8 milliliters. That means that we used 0.8 milliliters of the titrant solution. If you multiply that number by 10, that's how much dissolved oxygen is in the water. So we have 8 milligrams per liter of dissolved oxygen in the stream here. Next, since we've completed this test, we'll take all of our extra liquid and put it into our discarded sample bottle, and we'll take this back, like I said earlier, to the classroom to dispose of properly down a sink. The next 2 tests that we're going to do are for nitrates and phosphates. The nitrate test comes in this bag of material here, and the phosphate test comes in this little black container that says Hannah on the top from Hannah Instruments. So nitrates and phosphates are both nutrients that are essential for plant growth. They help have healthy roots and stems and flower production in plants. They're very important nutrients to the health of the landscape around our lakes, rivers, and streams. But if there are excessive amounts of nitrogen or phosphorus in our streams, it can cause overgrowth of algae, which can have toxic chemicals that it produces and can also suck oxygen out of the water as it dies and decomposes. So we don't want to have too much nitrogen and phosphorus in the water, so we're going to test and see how it looks. Now, the nitrogen test has some components where it needs to sit for a few minutes. So I recommend getting your nitrogen test started early, and then while the test is sitting, you can perform your phosphate and your other tests. For nitrogen, we're testing nitrates, and for phosphorus, in the field, we're testing orthophosphate. Now, phosphorus can be freely available to plants in orthophosphate, but there are also some organic phosphates that are bound up and unavailable to plants in the water, and we can only assess how much is in the water altogether by doing a total phosphate test. So we're going to do in the field orthophosphate, and our lab sample is going to test total phosphate for us. So let's start with the nitrate. You can start by taking out this little yellow piece of foam. This doesn't need to be in it. And this is going to be our holder for the test materials. The next thing you'll do is take out the foil package there, open it up, and put your 4, these are called cuvettes, put your 4 cuvettes into each of the 4 holders here. I'm going to put the garbage in my waste container. Let's flip this around. This one. You don't like that leaf? So we have these 4 cuvettes. You'll notice this cuvette in the front has a blue dot on it. That means that this is going to be our standard. So a standard is a known quantity of nitrogen in the sample that will allow us to make sure the sample test is working properly. So we're going to do some different steps with the standard than we do with the other 3. Now we are going to use water from 1 sample for these other 3, and we'll be performing the test in triplicate. You can also use 3 different water samples if you had samples from different locations that you could use in these cuvettes. All right, so this one has a lot of steps to it, and so it's very important that you follow the instructions closely, Jack. Make sure that you do exactly what it says. So the most important thing right off the bat is we want to try to keep these cuvettes upright as much as possible at the beginning. There is a little bit of reagent, that's enzyme, that's already in the cuvette that we don't want to disturb too much. So don't ever take these cuvettes and invert them until the instructions tell you to. Okay, so the first thing you're going to do is you're going to prepare the standard, Jack. So I want you to take this front one that has the blue dot on it, open the lid, and then we have this little squeeze bulb that also has a blue dot on it. This is our standard solution. So I'm going to twist the lid off of the standard solution and squeeze it into the standard bottle. Then you're going to put the lid on that. Don't invert it, just set it right back into the cuvette holder. Next, we're going to prepare our samples. So you can take the lids off these 3. And to each of these cuvettes, Jack is going to add 20 drops of this buffer solution. So 20 drops to each of these 3 cuvettes. All right, then you're going to put the lids back on the cuvettes. And then each cuvette you'll swirl gently while keeping it upright, just to make sure everything gets mixed in. That looks good. That looks good. That looks good. Now at this point, the cuvettes need to sit for about 10 minutes while a chemical reaction occurs. So we are going to just set this aside and we're going to move on to the phosphate test while we wait for that. We're going to look at our watches and see what time it is and set a timer for 10 minutes. All right, the next test we're going to perform is the Ortho phosphate test. So Jack, if you want to open up the test and show us the components inside. We are going to use a little device called a Phosphate Checker. I really like this test because when it's done, it just gives you a number that you can record at the end. So the first thing we're going to do is you're going to turn the instrument on. So press this black button 1 time, and you should see the screen say add C.1, okay? So we're going to set this down. The first thing you're going to do is take this glass bottle.
Do you mind holding the first thing again? Yes. Thank you. Perfect.
Does it still say that? Okay, good. All right, so take the glass, this is also called a cuvette, the glass bottle, and we're gonna fill that to this white line. Let me do this back here a little bit so I don't dump it on my, okay. Sorry.
It's on me.
All right, so you can put the lid on and then try to wipe off any excess liquid from the outside. And then we're gonna actually put this into the container without any chemicals in it to zero out the device. There we go. Sorry, I'll try not to break it. Okay. All right, so you always wanna make sure this is level. So you'll set it into the meter. Oh, no. Sorry. Back up. Put the lid on. We'll put the lid on the jar. And then with the lid on, set the whole glass vial into the meter. Then we'll close the lid and we'll press this black button one more time. So you'll see it will blink for a few seconds and then it should say add C2 in a moment. This can take anywhere from 30 to 60 seconds for the device to zero.
Okay.
All right, so now you see it says add C2. That means we're gonna take the glass vial out of the device and we're going to add some reagents, some chemical reagents to the vial. So the first one that we will add is the contents of one of these little packages that says reagent B. So you can open up the package and you'll dump that powder into the vial. All right, we'll take the rest of this package, put it in our trash. Oh, we're gonna add one more thing before you put the lid on. So we're also going to add 10 drops of this reagent A. All right, now you put the lid back on the vial and shake it up until the powder is dissolved. This might take a minute or so for the dissolving to occur fully. All right, how's it look? All right, that looks pretty good. It's mostly just little bubbles floating around in there. So again, making sure there's not any liquid on the outside of the glass, you'll take that vial, put it back into the device, where you can see it says add C2. So once you've added your sample C2 and press the button one more time, the checker will count down from 5 minutes. At the end of 5 minutes, it will give you a numerical value. In this case, we got 1.1, and that's parts per million of phosphate in the water. When that's complete, you can take your sample out of the vial and dispose of it in with the rest. You can take your sample out of the vial and dispose of it with the rest of our chemical waste, which we'll dump down the drain when we get back to the classroom. The next test that we'll prepare to perform is the fecal coliform test. So coliforms are bacteria that are found in the gut of warm-blooded animals. If we find them in the water, it helps us to understand that there's bacterial contamination in the water. So earlier, we took a sample that's going to be sent out to the lab to assess for E. coli. We're also going to do a sample back in the classroom of our own that we can compare to that lab sample. We're not going to perform that whole sample in the field. What we're going to do is I'm just going to show you the materials that you'll use. So in your kit, you have something called the ColiScan Easy Gel. And you are going to add somewhere between 1 and 5 milliliters of sample water to your Easy Gel container, depending on how much coliform you suspect is in the water. So if you think there might be a lot of bacterial contamination, you're going to add 1 milliliter of water. If you think there's probably not very much contamination, you'll add 5. And you can do multiple tests at different concentrations of the water to see how much bacteria is actually there. So you add your sample to the gel, you'll shake it up, and then you're going to put this in your cooler and take it back to the classroom with you. When you get to the classroom, you are going to open up one of these pre-treated plates and pour your sample in. Now, the reason we don't do this in the field is because it takes about an hour for that to gel and harden up, and we don't want to have to take a petri dish with water sloshing around all around in the car. So you're going to wait till you get back in the classroom. You're going to dump your solution into your dish. You're going to let it firm up for about an hour. Label on the top of the dish how much water you added to the Coliscan Easy Gel solution, and then you're going to incubate it at 20 degrees Celsius for 24 hours, or you can leave it at room temperature on the counter for 48 hours. And then you'll notice little bacterial colonies growing on your petri dish, and you're going to count the number of blue and purple colonies that form to get an understanding for how much fecal coliform, total coliforms, and how much E. coli is in your sample. All right, now that our cuvettes have been sitting for 10 minutes, we can do the last step of the nitrite test. So at this point, we are going to add a reagent that's found in these little tubes with the white powder to each of the 4 cuvettes, and this is going to cause a color change to occur. When that color change is complete, we'll compare it to a color chart to get our final reading. So at this point, I'm going to have you, Jack, if you want to do these two, we'll add these to each cuvette, one to each cuvette, even the standard one with the blue dot. So I'll do these two if you want to do those two. So you'll open up the cap. If the white material is stuck, you can tap it a few times to loosen it up. So you'll add it to your cuvette, and then you'll shake your cuvette to dissolve the reagent. At this point, you can invert and shake the cuvettes. So you'll shake them until the solid is totally dissolved. Takes a few seconds sometimes. It's okay if there's a little bit of it still floating around. And then we'll take these and we'll let them set. And sometimes it takes a few minutes for the color to fully develop. So you might want to wait for 5 minutes or so to let the color develop. But what you should notice right away, these are our 3 samples. And this dark pink one here, this is our standard. So we wanted our standard to be this dark pink color. So we're going to let these sit for about 5 minutes to let the color fully develop, and then we're going to compare them to our color chart. All right, so it's been 5 minutes that we've let this color fully develop. So it's time to read our sample. So this standard should match the 5 parts per million of nitrate standard. So we'll compare it to our color chart here, and we see this is what it looks like to have 5 parts per million. Then we'll take our sample vials and we'll hold them up against this chart and see which value they look closest to. So Jack, why don't you take a look? Which one, what would you say, looking at the color chart, that our sample matches up with?
I would have to say around right here.
Right there.
Right here.
Yeah, so right between, pretty close to 2 parts per million.
2 parts per million.
So with a color chart like this, it's not always incredibly precise. So the Michigan Department of Environment, Great Lakes and Energy has a few of these backpacks that you as an educator can check out that have all of the tools we've already seen in them, but they also have something called a photometer, which looks like this. This is a little device that can connect to your Android device via Bluetooth, and you can actually place your sample into the photometer, and it will use light to read the sample and give you an actual readout of the number, just like your phosphate one did. But if you're in the field using the backpack kit that you have and you don't have a photometer, this color chart is pretty good. So we would record 2 parts per million as our nitrate reading. All right, the last thing we're going to look at right now is turbidity. Turbidity is a measure of how clear the water is, and it can be affected by things like sediment, soil in the water, or by algae growth. So we're going to do this using what's called a turbidity tube. This tube is 120 centimeters long, and inside the tube there's a black and white disc at the bottom. Jack's going to hold the tube. I'm going to fill the tube all the way to the top with sample water from the stream. I'm going to try not to splash it all over you. Sorry. There we go. All right. Now the tube is totally full of water. Jack is going to stand over the tube and look straight down. Now, can you see the black and white disc at the bottom of the tube?
I can.
He can see it. So because he can see it, because it is able to be visible when it's totally full of water, we would record the turbidity of this sample as greater than 120 centimeters. Now, let's illustrate what we would do if you couldn't see to the bottom. So I'm gonna fill this back up a little bit. Sorry. Now, if he looked into this tube and he couldn't see the black and white disc, what he would do is gently push down on the tube until the valve at the bottom opens and water starts to pour out. And you would look directly over top until the black and white disc becomes visible. So let's say it's visible now. If you want to hold on to it, what we would do is if it took to here for the black and white disc to be visible, we would take out our measuring tape and we would measure the distance from the disc to the top of the water. So if this is how much water he had to let out to be able to see the disc, I would measure from here up to the water, and that looks like that is 85 centimeters, and you would record the turbidity unit as 85 centimeters. So that's it for all of our chemical tests that we'll perform in the field today. Our lab samples will head off to the lab when we leave the site. They'll take a day or two to come back, and then don't forget to record all of your results on the LGROW data map. Should I say something else?